Hello everyone. Today we're diving into the fascinating world of machine learning, specifically focusing on principal component analysis, also known as PCA, and its application in clustering algorithms like k-means. We'll explore the theoretical foundations of PCA, the importance of data standardization, and how to effectively determine the optimal number of clusters using various metrics. Let's start with PCA. PCA is a powerful technique in machine learning that originates from linear algebra. It leverages eigenvalues and eigenvectors to identify the principal components in an n-dimensional space with n features. These principal components are essentially new axes that maximize the variance in the data, allowing us to reduce the dimensionality of the dataset while retaining as much information as possible. One crucial aspect of PCA is the selection of the number of components. If we choose too few components, we risk losing significant information. A common practice is to select the number of components that explain 95% of the variance in the dataset. This approach ensures a robust reduction in dimensionality, transforming a high-dimensional space into a lower-dimensional one, which is beneficial for many machine learning models. Next up, let's talk about data standardization. Before applying PCA, it's essential to standardize the numerical features, example given the floats and the integers, because PCA is not scale invariant. Standardization ensures that all features are on the same scale, typically with a mean of 0 and a standard deviation of 1. The standard scaler from the sklearn.preprocessing module is a good starting point. While it may not be the best scaler for all situations, it is a reliable choice for initial experiments. On to application in k-means clustering. PCA is particularly useful when combined with k-means clustering. K-means can be sensitive to irrelevant features that do not explain much variance, making it harder to define robust clusters. By reducing the dimensionality with PCA, we can focus on the most relevant features, improving the clustering results. After standardizing the data and applying PCA, we typically select the components that explain 95% of the variance. We then run k-means clustering and test different numbers of clusters. To determine the optimal number of clusters, we use the elbow method, which involves plotting the inertia, the sum of squared distances to the nearest cluster center, and looking for an elbow point, where the rate of decrease sharply slows. However, the elbow method can sometimes be ambiguous. Therefore, we also use the silhouette score and the Kalinski-Harabas score. The silhouette score measures how similar an object is to its own cluster compared to other clusters, with higher values indicating better defined clusters. The Kalinski-Harabas score, on the other hand, evaluates the ratio of the sum of between-cluster dispersion to within-cluster dispersion, with higher values indicating better defined clusters. Let's conclude. In summary, the process involving standardizing the data, applying PCA to retain 95% of the variance, and then running k-means clustering by using metrics like the silhouette score and the Kalinski-Harabas score, we can determine the optimal number of clusters. While domain-specific knowledge can significantly enhance this process, the outlined approach provides a solid foundation for general-purpose clustering tasks. Thank you for watching, and we'll see you next time.